Section 1 Introduction. We're here to discuss the recent progress in large language models, LLMs, such as GPT-3, Gopher, Chinchilla, and PaLM 2L. These models, trained on vast amounts of unlabeled data, have shown impressive abilities in a range of tasks, from programming to creative writing. They can handle tasks with no prior examples, zero-shot, and tasks with a few examples, few-shot, quite well. Their performance can be further enhanced through a process called supervised fine-tuning, SFT. One strategy that has gained traction in this area is instruction tuning. This method uses datasets filled with instructions and corresponding human-written completions to improve the model's generalization and usability. However, getting the model to produce the desired outputs across different domains is still a challenge. To address this, a method called reinforcement learning with human feedback, RLHF, has been introduced. This method aims to better align the large language models with human preferences. However, RLHF introduces some complexities into the training process. For instance, incorporating a reward model and frequently sampling from the policy during training can require a lot of memory, which can limit the size of the model. Also, including rollouts in the training loop can slow down the optimization process, as it requires continuous model sampling and decoding. Moreover, fine-tuning the PPO process requires specialized knowledge. In light of these challenges, recent research has proposed alternatives to RLHF, such as RRHF, SLIC, and DPO. These methods aim to align LLMs with human preferences more effectively, while avoiding the complexities of reinforcement learning. Let's take a closer look at how these methods work. Given supervised fine-tuning data and preference data, RLHF first trains a supervised fine-tuned model and a reward model. Then, it applies a reinforcement algorithm like PPO to maximize the reward. On the other hand, RL-free algorithms use the preference data in different ways. For instance, RRHF uses a trained reward model or human raters to calculate rewards for multiple sequences generated from the same prompt. Then, it applies a ranking loss plus a supervised fine-tuning loss. They explore various ways of sampling sequences, such as beam search, online sampling, and iterative updates. SLIC, on the other hand, uses a contrastive ranking calibration loss plus a regularization loss for sampled and labeled preference pairs. Essentially, SLIC penalizes the model when the likelihood ratio between positive and negative outputs is less than a certain value, thus encouraging a large likelihood ratio between these outputs. Instead of directly using human preference data, SLIC proposes to sample pairs from the SFT policy and get them labeled by a pairwise reward ranking model. They show that this approach results in clear gains on a summarization dataset that are consistent over model size scaling up. While RRHF and SLIC offer scalable alternatives to PPO, they lack theoretical understanding. DPO addresses this by analyzing RLHF's objective function in the form of KL regularized reward maximization, and analytically solving the optimal policy induced by a reward function. DPO proposes a maximum likelihood estimator to fit on human preference data directly. It establishes a theoretical foundation that connects language model with preference model as a density estimation problem from the labeled response pairs. DPO expresses the human preference probability in terms of only the optimal policy and reference policy. However, DPO uses the collected human preference data from other policies directly in all the experiments and lacks study on the effect of sampling. In our work, we address these issues by constructing preference pairs from the approximated optimal policy. We start from a human preference dataset collected from other policies, train a pairwise reward ranking model, then apply a statistical rejection sampling algorithm to generate response pairs sampled from optimal policy. After that, we label the sampled response pairs by the reward model. Then we fit the model on labeled pairs via classification loss. Our contributions are threefold. 1. We propose a scalable and easy-to-implement framework to learn from human preference data. We provide a comprehensive recipe among different choices of loss functions and preference pairs generation. We show the importance of the reward model instead of directly optimizing the model on the preference data. 2. Statistically, we unify DPO and SLIC by showing that they vary by loss functions to fit on human preference data. DPO is a logistic regression on human preference data, and SLIC is almost equivalent to a support vector machine, SVM, with hinge loss. We improve SLIC as the SVM counterpart of DPO. 3. We propose a statistical rejection sampling algorithm to sample pairs from the optimal policy and get them labeled by a pairwise reward ranking model. The proposed sampling strategy is shown to be effective on 3 generative tasks. Section summary. Recent advancements in large language models, LLMs, have led to impressive capabilities in various tasks, and supervised fine-tuning, SFT, has been used to improve their performance. Reinforcement learning with human feedback, RLHF, has emerged as a promising approach to align LLMs with human preferences, but it introduces complexities and memory constraints. Alternative methods such as RRHF, SLIC, and DPO have been proposed to address these challenges and improve model alignment with human preferences. Section 2 Preliminaries. We'll start by discussing the concept of learning from human feedback. This approach has been shown to significantly enhance the performance of conditional language generation. Several algorithms, such as RLHF, RRHF, SLIC, and DPO, have been developed based on this concept. These algorithms require 2 types of input. The first is a supervised fine-tuned policy, which is a function that takes a prompt as input and generates a response. The second is a dataset of human preferences, which helps the algorithm distinguish between better and worse responses to the same prompt. Now, let's delve into the specifics of these algorithms. DPO, for instance, uses a simple strategy of fitting a logistic regression model to the human preference dataset to optimize the policy. SLIC, on the other hand, uses a max margin loss function to fit the human preference data, thereby improving the model's performance. A variant of SLIC, known as SLIC sample rank, first fits a model that ranks rewards based on human preference data, then generates response pairs from the supervised fine-tuned policy and labels them according to the ranking model. The SLIC loss is then applied to these generated preference pairs. RRHF follows a similar approach but ranks the sequences either manually by humans or through a reward model. The RRHF rank loss is then applied to refine the model based on these rankings. RLHF, however, first fits a reward model and then uses the PPO algorithm to optimize the policy. Next, we'll discuss the concept of the optimal policy. This is the policy that maximizes the reward. It is calculated as the supervised fine-tuned policy multiplied by the exponential of the reward divided by a factor beta, all divided by a partition function. This partition function is the sum of the supervised fine-tuned policy multiplied by the exponential of the reward divided by beta, over all possible responses. The factor beta controls the balance between exploitation and exploration. When beta approaches 0, all probability mass will concentrate on the max reward with full exploitation. When beta approaches infinity, the optimal policy will be the same as the supervised fine-tuned policy with full exploration. The reward function can be rearranged to show that it is equal to beta times the logarithm of the ratio of the optimal policy to the supervised fine-tuned policy, plus beta times the logarithm of the partition function. This equation establishes the relationship between the optimal policy and the reward function, and one can be inferred from the other. The ultimate goal is to have a good policy for response generation, and the optimal policy is usually of more interest. The challenge is to effectively estimate the optimal policy from the human preference data. Finally, we'll discuss the preference model. The optimal policy associated with the ground truth reward function can be represented by the equation we discussed earlier. For 2 responses from the same input, one can assume that the probability of one response being preferred over the other is a function of the difference in their rewards. This function is monotonically non-decreasing and converts the reward difference into a winning probability. If we set this function as a sigmoid function, we get the Bradley-Terry model. The reward advantage of one response over another is defined as the difference in their rewards, which is equal to beta times the logarithm of the ratio of the optimal policy to the supervised fine-tuned policy for each response. The probability of one response being preferred over the other is then a function of this reward advantage. This equation establishes a connection between the preference data and the optimal policy. If we use the human preference data to represent the probability of one response being preferred over another, the estimation of the optimal policy can be viewed as a density estimation problem from the preference data. We'll discuss different ways of estimating the optimal policy from the preference data in the next section. Section Summary. Several algorithms, such as RLHF, RRHF, SLIC, and DPO, have been developed to improve conditional language generation by learning from human feedback data. These algorithms take a supervised fine-tuned policy and a human preference dataset as inputs. Each algorithm employs different strategies, such as logistic regression, max margin loss, pairwise reward ranking, or reward model fitting, to optimize the policy based on the human feedback. The ultimate goal is to estimate the optimal policy for response generation, which can be achieved by establishing a connection between the preference data and the optimal policy using the Bradley-Terry model. Section: Policy Estimation on Preference Pairs. We're going to discuss how to estimate policies based on preference pairs. Two methods, DPO and SLIC, estimate the optimal policy, denoted as pi star, in different ways. DPO fits a Bradley-Terry model directly on preference data using a logistic loss function, while SLIC uses a contrastive approach to ensure the preferred option in a pair has a higher probability than the less preferred one. However, in statistical density estimation, the preference pairs should ideally be generated from pi star, the density we want to estimate. DPO and SLIC don't do this, instead using preference pairs from unknown or different distributions. This means neither method provides the maximum likelihood estimate of pi star, which is why we're proposing a new approach that can generate preference pairs from pi star. Let's talk about the reward model. Usually, this model assigns a score to a pair consisting of a prompt and a response. We suggest a simpler and more direct method, training a pairwise reward model using triplets of a prompt, a worse response, and a better response. This approach has been shown to be preferred in reinforcement learning free learning. In our work, we train a model to predict the probability that one response is preferred over another. For a summarization task, the input format is a context document, a positive summary, and a negative summary, and the output is either A or B. For AI assistant tasks, the input format is a context conversation between a human and assistant, a positive response, and a negative response, and again, the output is either A or B. We can derive the reward score of one response from the reward score of another response based on the winning probability. If we have a baseline sequence with a reward score of 0 and a fitted pairwise reward ranking model, we can estimate the reward score. In other words, we can derive a pointwise reward score from a pairwise reward ranking model with a baseline sequence. In practice, we choose a random decoded sequence from the SFT policy as the baseline. Now, let's discuss our proposed approach for estimating the optimal policy, pi star. Our system takes three inputs: the SFT policy, the reward ranking model, and prompts. We first sample responses from the optimal policy using a rejection sampling approach, then fit a classification model on labeled preference pairs. To evaluate our approach, we consider different options for the loss function and preference dataset construction. Given a preference dataset, we can estimate pi star. There are two things we need to consider: the choice of loss function and how to obtain the triplets for the preference dataset. For the loss function, we can use a simple binary classifier. The two most common choices are logistic loss, used in logistic regression, and hinge loss, used in support vector machines. For the preference dataset, we need to decide how to obtain the triplets. DPO proposes using a sigmoid loss on normalized likelihood to fit a logistic regression. By doing this, we can fully control the steepness of the logits function for classification. The larger the value of gamma, the more we penalize misclassified examples at the decision boundaries. SLIC, on the other hand, proposes using a hinge loss. We use 1 gamma as the margin delta used in the original SLIC paper. This is equivalent to a hinge loss with a certain logit. Section Summary. The section discusses two approaches, DPO and SLIC, for estimating the optimal policy pi***, using preference data. However, neither of these approaches are the maximum likelihood estimate, MLE, of pi***, because they use preference pairs from different distributions. To address this, the authors propose a new approach that obtains preference pairs directly from pi caret asterisk. They also introduce a pairwise reward ranking model and demonstrate its effectiveness in RL-free learning. Section: Choice of preference data distribution. Let's discuss how we choose the distribution of preference data. Ideally, we would have access to a perfect set of preference data, denoted as D. This data would allow us to directly apply a maximum likelihood estimation, MLE, to the dataset. However, in reality, we often don't have access to such perfect data. Instead, we have access to a different set of data, denoted as D_HF, which is influenced by a mix of unknown policies. These policies could come from various sources, such as the SFT policy, the current RLHF policy, policies from other agents, or even preference pairs mined from the web. In our research, we use human preference data sampled from other agents, such as OpenAI agents for the Reddit TLDR dataset and Anthropic agents for the Anthropic HH dataset. Given this D_HF data, we consider three different approaches. 1. Direct. This approach involves directly fitting the policy on the D_HF data. This is the method used in DPO. A similar variant, SLIC direct, was proposed in SLIC, but with a different loss function. 2. SFT sample rank. This method first trains a reward ranking model on the D_HF data. Then, it uses the SFT policy to sample response pairs and label them using the reward ranking model. This results in a preference dataset, D_P. This approach is the same as the SLIC sample rank variant proposed in the SLIC paper. 3. RSO sample rank. This approach also starts by training a reward ranking model on the D_HF data. Then, it uses a policy induced by the reward function to sample response pairs. These pairs are then labeled using the reward ranking model to construct the preference dataset, D_P. This method can generate samples that are closer to the ideal preference data than the other two methods. However, sampling from this policy is not straightforward, so we propose a statistical rejection sampling approach to achieve this. Statistical rejection sampling is a technique used to generate observations from a distribution. If we want to generate a distribution of density from the reward function, we can use the SFT policy as the proposal distribution. The process involves generating a sample from the SFT policy and a random number between 0 and 1. We then determine a minimum value, m, such that the SFT policy is always greater than or equal to the reward function. If the random number is less than the ratio of the reward function to the product of m and the SFT policy, we accept the sample. Otherwise, we reject the sample and repeat the process. This approach allows us to draw samples from the optimal policy by rejecting more samples in the low reward region and accepting more in the high reward region. Section Summary. In this section, the authors discuss the choice of preference data distribution for training a policy. They compare three options: direct fitting of the policy on the available preference data, using a reward ranking model to sample response pairs and label them, and using statistical rejection sampling to generate observations from a distribution closer to the optimal policy. The statistical rejection sampling approach is considered the best solution as it can generate samples closer to the optimal policy, but it requires a rejection sampling algorithm to achieve this. Section: Statistical rejection sampling algorithm. We're introducing a new algorithm, which is a practical version of the statistical rejection sampling algorithm. This algorithm is designed to generate a certain number of unique samples from a specific distribution. The algorithm's effectiveness is determined by the number of potential responses and the highest reward among the responses not yet accepted. As the number of potential responses increases, the algorithm's ability to generate unique samples also increases. The algorithm's performance is also influenced by a parameter we'll call beta. If beta is very large, every sample generated by the algorithm will be accepted. On the other hand, if beta is very small, only the response with the highest reward will be accepted, and all other responses will be rejected. The value of beta reflects how much we trust our reward model. If the reward model is highly accurate and reliable, we should use a small beta. If not, we should use a larger beta. In practice, we choose the value of beta based on validation metrics. Recent advancements in language learning models, such as GPT-3, Gopher, Chinchilla, and Palm 2L, have significantly improved their ability to perform tasks with little or no prior training. However, we can further improve these models by fine-tuning them on datasets that include instructions and human-generated completions. This approach has led to improved performance in various applications, including translation, summarization, storytelling, and following instructions. Despite these advancements, fine-tuning large language models with reinforcement learning remains a challenge due to instability, reward hacking, and scalability issues. To address these issues, we propose a new approach that optimizes for human preference feedback without relying on reinforcement learning. This approach involves training a model to be compatible with preference datasets, using models such as the Bradley-Terry model. We also propose a new way of collecting preference pairs using statistical rejection sampling, a method used to generate samples from a target distribution using a proposal distribution. This method involves selecting the top k-sampled candidates to collect human preference datasets. We show that this approach can deliver a maximum likelihood estimation for human preference data. We tested our approach on 3 different open-ended text generation datasets: Reddit TLDR summarization, CNN, Daily Mail, and Anthropic helpful and harmless dialogue dataset. These datasets contain a variety of examples, including online news articles paired with multi-sentence summaries and dialogues between a human query and an AI assistant. Each example ends with a pair of responses generated by a large language model, along with a preference label indicating the human preferred response based on helpfulness and harmlessness. We used the helpfulness task in our experiment setting. For each task, we used the positive response, the better one, as the target. Section summary. The authors propose a statistical rejection sampling algorithm, called algorithm, which can generate distinct samples from a target distribution based on a reward model. The algorithm's behavior is controlled by a parameter called beta, which determines the acceptance rate of samples. The authors also discuss related work on training language models using human preferences and highlight the challenges of reinforcement learning-based fine-tuning. They introduce their RL-free approach, which optimizes for human preference feedback with theoretical guarantees. The authors evaluate their approach on 3 text generation datasets and compare it with other models. Section. Method. Our method begins with a large T5 model and a T5XXL model, which we use to explore 9 different settings. These settings are combinations of 3 types of loss functions and 3 types of preference data distribution. The DPO approach from the original paper is equivalent to our sigmoid norm direct setting, while the SLIC approach is similar to our Hinge SFT sample rank setting, with a couple of minor differences. Firstly, the original SLIC paper includes a calibration loss and a regularization loss. However, we found that the regularization loss didn't significantly improve the final results, so we decided to drop it. Secondly, SLIC uses a tournament-style procedure to rank candidates. For instance, if we have 4 candidates, we first rank the first 2 and the last 2, and then rank the winners of those 2 pairs. In our case, we only use the first round of this tournament ranking, which are random samples from the SFT policy. Unless otherwise stated, we set beta to 0.5 and gamma to 0.05. For the statistical rejection sampling algorithm, we first sample 64 response candidates from the SFT policy, then subsample 8 samples. For SFT sampling, we start with 64 response candidates sampled, then randomly subsample 8 candidates without replacement. We use a batch size of 128 and a learning rate of 1E5 with the Addifactor optimizer. For each run, we select the checkpoint with the highest reward score according to the reward ranking model. Our experiments use 3 different approaches to evaluate the results. All of them involve side-by-side comparisons of the generated sequence versus the original SFT target. We report the win rate by 3 systems: the trained T5XXL pairwise reward ranking model, the Palm 2L few shot side-by-side, and human side-by-side. For the Palm 2L few shot side-by-side, we use in-context learning to infer 8 decoded samples with 4 flipped the order. The label contains 3 choices: A, B, and tie with score 1, 0, and 0.5, respectively. If the magnitude exceeds 0.35, we use the average score to determine the win or loss. The purpose of the PALM-2L few shot side-by-side is to prevent artificially high reward scores due to reward hacking on learned policies. Since the policy is trained using the information in the pairwise reward ranking model, a higher win rate on the reward ranking model doesn't necessarily mean a better policy. The PALM-2L few shot side-by-side has proven to be effective and consistent when using GPT-4 as a zero-shot rater. In this work, we replaced GPT-4 with PALM-2L for our evaluation using few-shot prompts. We found that the SFT sample rank consistently outperforms the direct method, and the RSO sample rank further improves upon the SFT sample rank. This is because when we fit the language model on preference data, the closer the data distribution is to the optimal policy, the closer the estimator is to the real maximum likelihood estimate. Therefore, the RSO sample rank results in the best performance. Regarding the loss function, we observed that sigmoid norm and hinge norm perform similarly, while hinge shows some extent of reward hacking with a higher reward model win rate but a lower auto-rater win rate. This is because the hinge loss relies too much on the reward function without considering any SFT policy. We provide examples with responses from different policies on Reddit TLDR and Anthropic HH tasks. Section summary. The authors started with AT5 large model and AT5XXL pairwise reward ranking model and explored different combinations of loss functions and preference data distributions. They found that the RSO sample rank setting resulted in the best performance, as it generated preference data closer to the optimal policy. Additionally, they observed that the sigmoid norm and hinge norm loss functions performed similarly, while the hinge loss function showed some reward hacking behavior. Section. Effect of gamma and beta in RSO. We're going to delve into the impact of two variables, gamma and beta, in the rejection sampling optimization (RSO) process. First, let's look at gamma. We kept beta constant at 0.5 and experimented with gamma values of 0.005, 0.05, and 0.5 in the loss function on the Reddit TLDR dataset. Our findings showed that a gamma value of 0.05 yielded the best results. Next, we turned our attention to beta. We kept gamma constant at 0.05 and experimented with beta values of 0, 0.05, 0.5, and 5 on the same dataset. Here, a beta value of 0.5 proved to be the most effective. Interestingly, a beta value of 0 aligns with the rejection sampling algorithm we've previously discussed. This suggests that blindly trusting the reward without regularization in the constraint reward optimization isn't always the best approach. We also wanted to understand the impact of different sampling strategies. We compared the results of using all 64 samples in the calibration versus using only 8 samples. We found that using a tournament ranking approach, which introduces bias towards higher reward sequences, consistently improved the reward model across different settings. However, it didn't improve the win rate in the case of 8-sample RSO. The best approach, according to the Auto SXS metric, was to use the first round rank of the 8-sample RSO. We also conducted a human evaluation using Amazon Mechanical Turk. We presented raters with a document and 3 responses generated from direct, SFT sample rank, and RSO sample rank methods. The raters were asked to assign a quality score to each response and choose the best one. Each task was performed 3 times by 3 different raters. To avoid bias, we anonymized all the models and randomly shuffled the order of responses for each task. In total, 47 different raters participated in the study, with each rater completing a median of 16 tasks. The results showed that the RSO sample rank method outperformed the other 2 methods across all loss functions and tasks, with a clear margin of improvement. When comparing 2 loss functions, sigmoid norm and hinge norm, we found no clear winner when applying the RSO sample rank method. This suggests that both the improved loss on SLIC and the original loss DPO perform similarly.